Hi, welcome to my talk, and thank you for joining CHIUW in a virtual format this year. I'm Rahul Ghangas, and I'm a student at the Australian National University, and today I'll be giving a talk on Chapel on Accelerators, which is based on a project with a similar name. My supervisor for this project is Dr. Josh Pilthorpe, who is an academic at ANU. A little bit about myself. I'm a final semester student at ANU. I do Bachelor's of Advanced Computing R&D. And I'm working with Chapel for my honors thesis. I've been a Chapel enthusiast for a while now, and I've been fascinated by the concepts that it has. And I see myself using Chapel on a regular basis in the future. When starting with a project, there's always the motivation, the big why, and this slide tries to do justice to that why. The advent of GPUs has been a different point in compute hardware. Although CPUs are very good at code which has high branching or divergence, GPUs are very effective for certain kinds of code, specifically exploiting parallelism by employing a large amount of mediocre compute units. Today, GPUs have become synonymous with high performance computing. Most of the top supercomputers use GPUs, including crazed new exascale systems like Aurora, Perlmutter, etc. So Chapel, currently not having native GPU support, leaves a lot of the performance on the floor. Introduction of C interoperability mitigated part of the issue, but that still leaves us with the two-language problem or the multi-language problem. This has been a highly debated concept in both academia and industry about how using multiple languages for a large project puts a large cognitive load on the programmer and hinders productivity. And often it is hard to cleanly carry over concepts from one language to the other, leading to loss in both user and compiler optimizations. The multi-language problem was one of the first ones that Chapel solved by making it possible to write parallel distributed applications from low level to high level in a single language. Chapel has easy to use high-level constructs built on top of low-level parallel patterns like map, reduce, etc. And GPUs can be effectively used for such patterns. Some of these high-level constructs include reduce expressions, operator promotion, data parallelism using for all loops, and task parallelism using co-for all loops. We started our exploration by doing a survey of previous work done by the AMD group back in 2017. We started with the reduction expressions and tried making it work with the current state of the compiler. We soon found out certain limitations with the AMD approach, such that they only allow single arrays to be used with reduced expressions. We extended support for complex expressions, such that complex promoted expressions can be offloaded to the GPU at the same time in a reduction kernel. We also introduced the concept of inferred intents for OpenCL kernels, where compile time constants are inferred and baked into the kernel directly. Runtime constants are passed in as OpenCL constants, allowing architecture to utilize cache instead of global memory. Another experimental optimization that we thought was splitting and transferring arrays to local memory based on the number of accesses to the array. Chapel has been gradually moving towards making LLVM the default compiler backend. So we also shifted our focus to LLVM IR. The idea is to directly emit IR kernels and generate corresponding host code. This maps to LLVM IR for NVIDIA and AMD GPUs using the NVPTX and the AMD GPU backends, and a SPIR-V intermediate representation for Intel GPUs. Next, we wanted to extend support for offloading for all loops onto the GPU, and this graph tries to describe our implementation. We extend or reuse the compiler provided for all statement types and wrap it in a conditional, where the conditional test value is the current sublocale on which the code is being executed. If the current sublocale is CPU, it gets executed on the CPU in a traditional manner, how CHIUW's been doing it. If the current sublocale is GPU, we check the GPU, we check the body for whether it conforms to a certain subset of CHIUW, and if it does, we generate and insert into the AST a block statement which contains host code and the kernel as a function symbol, which is then removed from the AST at code generation and emitted as an IR kernel. We want to define a concrete subset of CHIUW, a concrete specification that can be used on GPUs. And the idea has been something like disallowing external function calls, on blocks, co-begin statements, nested parallel loops, and also restricting array usage to index expressions only. We also want to let the users define their own workgroup sizes. And for this, we thought about two approaches. Approach one, we wrap for all loops in co-for all loops, where the iterated expression defines the number of workgroups in each dimension, and in turn also describes the workgroup size. And the second approach is providing language extensions to support defining workgroup sizes using with intents. The second approach is similar to what AMD proposed back in 2017. Lastly, at the start of this project, we wanted to push CHIUW to its limits and see what's the maximum we can squeeze out of it. This resulted in the GPUArrays library, which is a wrapper around normal arrays and allows lazy evaluation of promoted arithmetic operations. So basically, at each promoted operator, it builds up an intermediate representation and keeps on building on top of it on subsequent operators. Currently, it uses strings as the intermediate IR, but surely we can do something better. Finally, the array is computed when the user calls compute on a specific array. A sample code snippet can be seen on the left-hand side. Thank you. That